Okay, here's Thanasis Dimoulas again, and I would like to start the next session, the evening session, and our first lecturer is Mikhail Otrokov, who is a research fellow at Matthias Physics Center in San Sebastian. He obtained his PhD in condensed matter physics in 2011 at Tomsk State University, and then he moved to San Sebastian as postdoc, first at the Donostia International Physics Center and now at the Matthias Physics Center. So Dr. Otrokov, if you are ready, please share your screen.
Well, first of all, thank you very much for the nice introduction, and good afternoon, everyone. I will now try to share my screen. Here it goes. I hope you can see it. Can you see the screen?
Perfect.
Yes, it's okay.
Okay, great. So I'm ready to start whenever everybody is ready.
That's fine.
Okay, so I will start. Once again, good afternoon, everyone. My name is Mikhail Otrokov, or Misha for short. And today I'll be talking about magnetic topological insulators and heterostructures. But first of all, I would like to wholeheartedly thank the organizers for inviting me to give this tutorial. I'm really happy to deliver it. So let's start. Here is the outline of my talk. I will first start with a brief introduction on non-magnetic topological insulators. And after that, I will cover in many details the aspect of making non-magnetic topological insulators magnetic. Namely, I will answer the question why we would like to do this, and the most importantly, how people are doing this or have been doing this during the last 10 years or so. In the next large part of my talk, I will present the recent interesting results on novel magnetic heterostructures and explain why it is interesting. And before I conclude, I will also present the part about intrinsic magnetic topological insulators, materials that combine both magnetism and non-trivial topology intrinsically. So let's start. A non-magnetic topological insulator in 3 dimensions is a material whose bulk is gapped, while its surface is almost necessarily gapless. Why does it happen? The answer is due to spin-orbit coupling. Let us consider this on the example of a model topological insulator, which is bismuth selenite. Its crystal structure is shown here. It is composed of the so-called quintuple layer units made of selenium, bismuth, and selenium again, atomic layers. And here you have the so-called van der Waals gap, where the bonding is primarily of the van der Waals type. So this is a block layered material. As far as the electronic structure of it is concerned, it is a narrow gap semiconductor, both without spin-orbit coupling and with it. So let us now consider what kind of effect spin-orbit coupling has on the electronic structure of this material. With no spin-orbit coupling, the valence band maximum and conduction band minimum are contributed mostly by selenium and bismuth PZ orbitals, respectively. But once you switch the spin-orbit coupling on, I'm sorry, going too fast, this sequence gets inverted around the gamma point and exactly at the gamma point. But otherwise, in the rest of the Brillouin zone, it stays as it was. So this is what is called the bulk bandgap inversion due to spin-orbit coupling. And there is a theorem that states that if the bulk bandgap of an insulator is inverted due to spin-orbit coupling, its surface will be gapless. At least this is true for the so-called strong topological insulators. So this is how these gapless state, surface state looks like in the DFT calculation. It is called topological surface state because it is located in the bulk band gap. This is the valence band projected bands on the two-dimensional Brillouin zone. This is the conduction band. And this is how this topological surface state looks like in the experiment, namely angular result photoemission spectroscopy. As you can see, the dispersion of this state is practically linear, whereby we call it Dirac cone. One of the peculiar properties of this state is that it is very robust in a sense that unless you disrupt the bulk topology, you cannot get rid of this state, whatever you're doing with the surface, or practically whatever. For example, you can deposit adsorbates, you can create weak disorder at the surface. It doesn't matter, the state will stay there, although you will change its dispersion somehow. Another interesting and fascinating property of this state is that it is spin polarized, although being non-magnetic. This is because the time reversal symmetry is preserved, as it is expressed here, meaning that for each plus k parallel, where you have electron, let's say with spin up, there is a time reversal symmetry partner, which it is called in this way, at minus k parallel with a spin down. Eventually, all of these two spins compensate each other. The system stays non-magnetic, but the state is spin polarized. Moreover, this time reversal symmetry protects the electrons in the topological surface state from the elastic backscattering, because to backscatter, or in other words, to change the direction of the movement, of the motion on the opposite, you have to flip the spin, but this is not possible without magnetic perturbations. So basically, the electron of the topological surface state propagates with only one momentum, and it cannot backscatter. So you can see here this sketch, which is typically shown to illustrate how the electrons of the TSS move. So this immediately hints at some applications in dissipation-less transport, because electrons do not backscatter. So the question is, why do we want to break this time reversal symmetry? Why do we want to get rid of this apparently nice property? And there are good reasons for that, as I will explain in the following slides. So making non-magnetic TIs magnetic. How can you do that? Just for short, before going into details, you can either apply external magnetic field, which is actually not very practical, or you can try to organize magnetic ordering in a TI or at its surface. Typically, people are looking for ferromagnetic ordering. And in this case, the out-of-plane easy magnetization access is particularly interesting. Why? Because it can help you to introduce the exchange splitting in the topological surface state, which will manifest itself in the appearance of this so-called Dirac point gap. And once you have achieved that, you can try to realize in experiment a number of fascinating and practically promising effects. For example, quantum anomalous Hall effect or topological magnetoelectric effect, etc. Let us consider the quantum anomalous Hall effect in details. This is an effect that is observed in a two-dimensional time reversal symmetry magnetic system, generally with a non-zero magnetization. The system's band structure should feature the inverted band gap, which could look like this, for example, like two Mexican hats. Since the band structure is inverted due to spin-orbit coupling, this is a sort of topological insulator. And therefore, due to the bulk boundary correspondence, its physical edge should host the topologically protected mode. In this case, this mode would be one-dimensional because the bulk of the system is two-dimensional, and the mode would be chiral, meaning that at a given edge, the electron can only propagate towards one direction, and it cannot backscatter because, as it is illustrated here, for example, the left moving carrier is located physically at the one edge, while the right moving channel is located at the opposite edge. Therefore, electrons only have two possibilities. Either they go around the the film perimeter, let's say, and this is how they can end up moving at the opposite edge, or they tunnel through the bulk of the two-dimensional film, but it is insulating in principle, right? So therefore, the transport essentially occurs here. The quantized observable in the effect is the so-called Hall conductivity, sigma xy, which is quantized to integer multiples of E squared over h, and simultaneously the longitudinal conductivity, sigma xx, must be 0. This factor C here is actually a topological invariant corresponding to the number of the chiral edge modes in the sample. Why it is a topological invariant? Because in this case, it does not matter how, for example, large this gap is, what is the detailed dispersion of it, or basically it doesn't matter what kind of dispersion all the material has. Once there is a bulk Bandgap inversion in this sense, in the magnetic sense, the C will be equal either to 0 or 1 to 2, and will stay like this. Another effect, topological magnetoelectric effect. Imagine a 3D topological insulator with all its surfaces completely gapped. This can be either due to magnetization and or quantum confinement, for example. In this case, if you apply an external electric field to your system, it will respond with an additional contribution to the magnetization, which is quantized. And vice versa, by applying external magnetic field, you will induce electric polarization in your system. Once you have, how do you do that? First, you should induce the Dirac point gap, as I explained previously. Then you place the Fermi level exactly here in this gap. And then at a certain thickness, which is for bismuth telluride type topological insulators is about 20 nanometers, as far as I remember, you can be in the quantized regime. So the film thickness should not be too thin, let's say. And once you have achieved those conditions, you can try to realize nice consequences of this TME, topological magnetoelectric effect, such as image magnetic monopole. You can even think of memory elements based on this effect, or you can try to measure the magneto-optical quantized effects. By the way, those latter have been measured already in the case of non-magnetic 3D TI, but under external magnetic field, while without this field, that is in a purely magnetic topological insulator, there were only some hints of such magneto-optical effects of topological origin that were observed in the quantum anomalous Hall state of this chromium-doped BST. So how do we break the time reversal symmetry? How do we introduce magnetism? The most easiest way to do that is to grow non-magnetic topological insulator and then throw some magnetic atoms on its surface. In theory, everything works perfectly because, as it is said in one of the first publications on this topic, the magnetic atoms uniformly deposited on the surface of a topological insulator could naturally form a ferromagnetically ordered film. And indeed, if you perform an ab initio calculation, this is a model calculation, I believe, in this paper. But if you model in ab initio your chromium atoms regular arrays on top of bismuth selenite, for example, you will find that the system is ordered ferromagnetically and its easy axis is pointing perpendicular to the surface, which would induce a small but finite Dirac point gap at this coverage. So everything looks perfect. But in practice, it appears to be much more complex, and there was actually a lot of controversy concerning this subject. On the one hand, one group of Rps studies reported on gap-like feature near the Dirac point, which could look like this in the case of iron deposited on top of bismuth selenite. On the other hand, the X-ray magnetic circle dichroism measurements have found no proof of the long-range ferromagnetic order in such kind of systems. And correspondingly, there was another group of Rps studies that reported no Dirac point gap opening, as it is shown here. Actually, the reason of the absence of the long-range ferromagnetic order might be a strongly non-uniform distribution of these atoms at the surface that tend to form clusters once their coverage exceeds, let's say, about 10% of the monolayer. So there are basically two challenges to realize to open the Dirac point gap at the surface of Ti. You should achieve uniform Astrabat distribution, and you also take care to localize the Astrabat at the surface, because otherwise it can't penetrate below it. Or you can use this latter as an advantage and organize this near surface alloying, near surface doping. This has not been considered in the experiment with manganese, for example, only in theory. And the theory predicts ferromagnetic ordering up to the Curie temperature of 12 K, and the Dirac point gap of about 16 millielectron volts is opened, as reported by Henke and co-authors. But experiments performed in this case for iron atom depositions, no confirmed Dirac point gap, unfortunately. Other ways have been explored. Therefore, there is another variant of the magnetic doping that actually worked, in the sense that the quantum anomalous Hall effect has been observed. What kind of doping is this? In this case, you aim at uniformly dope the whole volume of a Ti film or a single crystal, and hope that the system will be ordered ferromagnetically. And this is exactly what happens with these chromium-doped bismuth antimony telluride films. They are films about 6 quintuple layer thick, 6 nanometers. Which order ferromagnetically with a Curie temperature of about 15 K, as reported by Chang and co-authors. And you see here the fingerprint of the quantum anomalous Hall effect, because the Hall conductivity at zero field, this blue curve here, achieves a quantized or almost perfectly quantized value of E squared over H, while the longitudinal conductivity is strongly suppressed. Basically, this is the reproduction, an experiment of this theoretical sketch. The value of E squared over H means that C is equal to 1. There is only one chiral mode propagating along the edge of this sample. Unfortunately, back then, the observation temperature was only about 30 millikelvin, but within 2 years, a huge leap of almost 2 orders of magnitude was observed thanks to this so-called modulation doping technique of the epitaxial growth of magnetic topological insulators. You basically dope the subsurface quintuple layer block of the material. In this case, as you can see, at 0.5, at 1 kelvins, the effect is perfectly quantized, and it deviates slightly from the quantized situation at 2 kelvins, but basically you can see the quantum anomalous Hall effect is there. So this was reported by Mogi and co-authors. The Curie temperature of this system was about 80 kelvins. So basically this is 2 orders of magnitude larger than the observation temperature. So what is going on there? What is the reason why we cannot go higher? The reason is very simple. These materials are very inhomogeneous. Starting already with an original non-magnetic composition, which is bismuth antimony telluride, you can see that this form of writing, it suggests that this is a random, let's say, random alloy in the pnictogen sublattice. Why do we mix antimony and bismuth? Because we need to tune the Dirac point where we expect to induce the gap later on by adding chromium. We need to move this Dirac point closer to the Fermi level. And this is achieved by adding bismuth actually to antimony, because antimony is only slightly p-doped, antimony telluride, while bismuth telluride is quite heavily n-doped. But as you imagine, since those 2 atoms are distributed quite randomly over the sublattice, the electronic structure fluctuates across the surface, which in particular translates into the surface location dependent Dirac point gap binding energy. Dirac point gap is moving across the surface, its binding energy is changing. Then you dope chromium atoms there, you increase the disorder. What happens in this case? Dirac point gap size is isn't homogeneous across the surface, as well as you can see in this nicely measured STS map of the Dirac point gap. Sometimes it reaches quite big, large values of 50 milli-electron volts, but across the surface, as you go, let's say, from one corner to another, it can go all the way down to 0. On top of that, the centers of all these gaps are not aligned. It is very difficult to achieve the global gap throughout the whole film. Basically, it can be, I don't know, whatever, micro electron volts or sub-milli electron volts for sure. And this is why the observation temperature is so low. So it's kind of very difficult to go higher with this approach in terms of the observation temperature. On top of that, some time ago, people discovered that these materials are not actually ferromagnets, although they show macroscopic fingerprints of a ferromagnet, which is a hysteresis loop, for example, here in the transport measurements and also in the magnetometry, discrete magnetometry. For example, if you focus on these points E or H, where the saturated values of the whole resistivity are achieved, you can see that the magnetization is not uniform. This is, by the way, is measured by this nice squid on a tip device, which allows you to resolve the regions within, let's say, 20 nanometers range. You can see that there are fields of both directions at the saturation, at the near the coercivity, where the remagnetization occurs. Actually, this process of remagnetization proceeds via the random flipping events. These islands, they flip independently. So it doesn't look like in a normal ferromagnet where one domain, which is aligned with the magnetic field direction, grows at the expense of the domain with the opposite direction of magnetization. It doesn't look like this. So it's a kind of super paramagnetic behavior, meaning that it is quite difficult to control the properties of such systems. Therefore, magnetic proximity effect was considered in particular as a viable alternative to the magnetic doping. In this case, one aims at inducing the finite magnetization in a TI through the interface coupling to a magnetic insulator, which is trivial. A number of systems were considered along this research direction. This is the not exhaustive list. But one of the most studied systems appears to be the europium sulfide bismuth selenite, for sure. Such a nice and beautiful interfaces have been formed as visualized by transmission electron microscopy. And you see the interface is almost perfect, at least at this scale. And importantly, a signal compatible to room temperature proximity effect has been measured, as far as I remember, by a spin polarized neutron reflectivity technique and reported here by Jagadesh Mudera group. Later, Mudera group and Zahir Salman group from PCI Zurich, they performed muon spin rotation experiments, and the conclusion was that most likely this signal was coming from stray fields originating from europium sulfide magnetic domains. And more recently, a nice XMCD experiment was performed in the group of Sergio Valenzuela and Adriana Figueroa here is first author, one of the organizers. And by nicely designing the measurements in different setups, different systems, films and thicknesses, the conclusion was that the XMCD does not detect the magnetic moments induced on bismuth, antimony, tellurium, or selenium. At least these magnetic moments, if there are, they are below the detection limit. So this system for sure needs to be investigated, needs to be understood what is going on there. But one of the things that would be nice to have is the electronic structure of such interfaces. But unfortunately, it is not very easy to do, at least with conventional Rps, because this interface is buried. You have to measure, let's say, various nanometers below the surface, but the Rps is essentially, at least conventional one, is essentially and surface sensitive. I think I have one question, so let's have a look. then is the notion that Tc is about 80 Kelvin is incorrect. You mean in the light of the data about superparamagnetic behavior? I don't think it is, well, yes and no, because let's say if you perform macroscopic measurements such as transport or magnetometry, you will have some critical point defined there. But if you measure with muon spin rotation technique, this is true that such systems actually show things like partial magnetic volume far above the critical temperature, as far as I remember. So actually, this is a very insightful question. So if you are interested, please check the, if I can go back, please check this publication by Zahir Salman Group and Jonas Krieger, PRB, 2017, or ask me, I will provide you the reference. Okay, I believe this is answered. So I can go further. Since it is very difficult to measure the electronic structure in experiment, the FT calculations can provide important insights in this sense. And these calculations have been performed. And for such systems like europium sulfide or manganese selenite interfaced with bismuth selenite, as it is shown here, the result was that apart from the Dirac cone, which survives, now it is a topological interface, not surface, but interface state, there are trivial interface states that appear due to the strong interface potential arising because we contact two systems that are too different. One is the block layered van der Waals material topological insulator, bismuth selenite, and another one has nothing to do with van der Waals coupling. The composition is different, the stoichiometry, etc. So there is a strong interface potential. Actually, it is this potential that causes the Dirac point gap to be small, because topological surface state tends to escape from the interface. It dives in the second septuple layer. And needless to say that once these trivial states have appeared, they close completely the gap induced in the Dirac point. So this is the material is useless for any kind of topological effects. So these are the challenges that has to be overcome. But luckily, the quantum anomalous Hall effect has been realized in the proximity magnetic effect type insulator in this nice sandwich heterostructure, zinc telluride chromium doped, and this is BST. And to complete the sandwich once again, the ferromagnetic insulator. You can see the quantum anomalous Hall behavior is here. And I believe the maximum observation temperature was about 0.1 Kelvin. So very nice result. Hopefully it will be reproduced by other groups, and hopefully we will see other reports of the quantum anomalous Hall effect in this type of magnetic topological heterostructures. But so far, as we have seen, the observation temperature of the quantum anomalous Hall effect at most reaches 2 Kelvin, or most strictly it would be around 1 Kelvin. So other platforms for the realization of the effect would be highly desirable. And one of those appeared some time ago, which is manganese bismuth 2 tellurium 4. I will call it MBT for short in the following slides. And also the materials based on this system are promising. I will tell you just in an instant. So for the first time, this material was synthesized back in 2013 in the powder form by Lee and co-workers, as reported here. Actually, they were mostly focused on the thermoelectric performance of the system. So they didn't study magnetic properties or electronic structure. But of course, they characterized the crystal structure, and they found that it is a block layered compound composed of these septuple layer block units. with manganese layer being in the center. And those septuple layers are connected by the van der Waals forces. Therefore, we have here van der Waals gaps. And you can see that this structure is pretty much similar to that of bismuth telluride. Actually, the lattice constants are very similar. I mean, the lateral ones. And you can think of a septuple layer block as of a quintuple layer block of bismuth telluride with a manganese telluride inserted in the center of it. Okay. So first, in the topological insulator context, these films were studied. Okay, I'm sorry, I think I have a question, maybe two. No, it's just chat. Yeah, the one question from anonymous attendee is how bands are inverted. I'm not sure that I understand the question and what part of the talk it is about. So could you please make it more specific, and I would be happy to answer the question. Next question, Nutachai Jutong. I do calculation with bismuth selenite europium sulfide in bulk. Surprised me, I found high Rashba splitting. So what do you mean by bulk? So you don't have surface? And then the question continues. The potential and the topmost terminate play very important. My question, is it possible to found it in experiment? Could it be checked by experiment? Well, I guess if you have some Rashba splitting, it should be somehow at the interface between the two systems. Then you should make this interface accessible to the conventional Rps, or at least laser Rps, which has larger bulk sensitivity. The soft X-ray Rps, I'm not sure that it will be helpful, because as far as I understand, it only works on the almost perfect single bulk single crystals, for example, or almost perfect interfaces. I'm not sure that in experiment, this interface will be as perfect as it would be desired for the soft X-ray Rps measurement. But okay, this is what I think. I hope I have answered your question. So I continue. So first thing that was done in the context of topological insulator business with this material was to consider its thin films on top of non-magnetic TI. Basically, we did it because it was simpler than studying MBT in bulk, which we were also doing back then, but it is much more challenging. But I will tell about this a little bit later. So here I would like to illustrate one concept which was called magnetic extension. So what is this? We started from depositing theoretically in DFT calculation, because this is what I am doing in my research. Depositing a single septuple layer film of manganese bismuth telluride on top of bismuth telluride surface. We have studied the magnetism, and we have found that it is ferromagnetic with the moments pointing perpendicular to the surface. So it looks quite attractive to try to split the Dirac point gap of the bismuth telluride surface state, which is this one with its characteristic dispersion. Dirac point resides well below the valence band maximum. Then what happens if you put this guy on top of the TI? The Dirac point splits gigantically, about 80 electron volts, and favorably, almost completely, this Dirac point gap resides within the fundamental bulk band gap. So in principle, you can use this for the quantum anomalous Hall effect. At least in theory, it's quite kind of attractive. What is the mechanism of this Dirac point gap splitting? It appears to be the penetration of the topological surface state into the magnetic film, as it is shown here. This is the z-coordinate dependence of the topological surface state charge density in the real space. This is integrated over the xy plane for each z point. And you can see that the magnetic block starts here, and we have here the large density of the topological surface state. And here it is not very large actually, but there is the huge magnetic moment of manganese, huge as compared to, let's say, induced magnetic moments on tellurium and bismuth. And in any case, it appears to be enough to open this large Dirac point gap. Apart from that, you see that there are no trivial states in the gap, in the whole Brillouin zone in this region. Why there are no? Because there is virtually an interface. The systems are very similar, very close one to another in terms of composition, structure, lattice constant. So this is why we have called, due to all those reasons, this approach magnetic extension, because the topological surface state recognizes this physical extension of the surface by the magnetic field, and it penetrates there. So it extends there, if you wish, magnetic extension. It is interesting to compare this approach to the, okay, I have one more question. What kind of DFT calculation can be used to predict a bandgap of 77? Yeah, well, in this case, this was a WASP calculation, projected augmented wave method, but I believe you can reproduce it with, let's say, FLPW or other methods. For example, other pseudo-potential method would be LKO, siesta code. So I don't think it really depends on the, sorry, it was about functional, yeah. That was GGA plus U. Well, if you wish, I will extend a little bit. GGA plus U, we found that it works pretty reasonably for manganese bismuth telluride in bulk. What do I mean is that we have been able to predict correctly both magnetic ordering, magnetic anisotropy, critical temperature based on the ab initio input, bulk bandgap. So I believe this is quite convincing, and we can use GGA plus U. We apply Hubbard Q on the 3D manganese states. Yeah, and then if you wish to use it for the thin film, it works, I believe, just fine, because we have tested it in bulk. Which pseudo potential you have used? Well, yeah, if you want me to be so specific, it was Perdue-Burg-Enzerkov pseudo potential, PAW in WASP. If this is your question, the answer would be like that. Thank you, everybody, for the questions. If you have more, please don't hesitate. And in the meantime, I will continue. Let us compare magnetic proximity effect and the magnetic extension. In the first one, and in the former, the small but finite magnetization is induced in the topological insulator, but as it is explained, and actually this is found based on the ab initio calculation in this publication, topological surface state escapes from the interface, at least in the case of manganese selenite or European sulfite, I believe, too. And this is why the Dirac point gap is small, because there is little overlap between the magnetization and the charge density of the TSS. On the other hand, in the magnetic extension case, the topological surface state propagates into the septuple layer block, or whatever block is this, and there it interacts with the local magnetization that are large manganese magnetic moments, and therefore the gaps are large, and they can be different combinations of the TIs and magnetic insulators. We have even tried MST back then, which has later been synthesized in experiment. More about that just in a few minutes. Yeah, more or less at the same time, there was.
Excuse me.
Yes, tell me, yes.
Excuse me, interrupt you. Perhaps the first 35 minutes have passed, So perhaps we need to make a short break or also allow to ask questions.
Unfortunately, I could not
Hello?
hear you very well, but yeah, it is about the break. Yeah, we can have a break to answer the questions in particular, right?
Yeah.
Okay, so there are questions. I will read them out. What about the gap? The question from Henry. What about the gap for in-plane orientation? I'm sorry, it seems to be the sound seems to be retarded, so we overlap sometimes. I will continue, right? What about the gap for the in-plane orientation of the magnetization? Well, generally, there is no. Although there are exceptions that have to do with symmetry constraint. I cannot reproduce it now by heart, but it has to do with the mirror plane, and if the magnetization is directed in one or another way with respect to this vertical mirror plane, there will be gap or not. There is a literature about that. I think the reference is Chao-Xing Liu, PRL 2013 or 11, something like that. Chao-Xing Liu, and I think Shucheng Zhang is also co-author. I will cover this in-plane magnetization case in some particular aspect in the following slides. Young, how do you control between magnetic proximity and magnetic extension effect? Well, magnetic extension is when the topological surface state penetrates inside the magnetic overlayer. So I believe you should calculate the topological surface state charge density and see how does it behave. Because, for example, as far as I remember, if you put chromium triodide on top of bismuth selenite, chromium triodide is a famous material with magnetic chromium there. If you put a single triple layer, right, of this material, it is also layered van der Waals material. But since the systems are different, the magnetic extension effect does not take place. So the topological surface state hardly penetrates there. If you are interested, it is a reference is Petrov 2019 jet platters. Oh, maybe I can even type the reference. Petrov 2019 jet plat. Shailia, I'm sorry if I'm not pronouncing the names correctly, guys. Magnetic field explicitly breaks TRS. In non-magnetic topological insulators, when we perform transport properties, we study in presence of magnetic field. So how does topological surface state preserve TRS? Well, if you measure under external magnetic field, it doesn't preserve TRS, and if you increase the magnetic field strongly, so there will be kind of Landau levels. So it's a time reversal symmetry breaking case, I believe. Anonymous attendee, how band gap arises in topological insulator? Like at first, how bands are inverted. So let me answer in the following way. If we are talking about the bulk of a topological insulator, it doesn't matter whether it's magnetic or not. The inverted band gap eventually arises due to the spin orbit coupling. Once the bands without the spin orbit coupling overlap, for example, or they do not overlap, but spin-orbit coupling has such an effect that they overlap, and then the avoided crossing effect appears, or the bands overlap due to the exchange splitting, and then spin-orbit coupling opens the band gap, or if exchange splitting does not overlap them, spin-orbit coupling maybe does, and then once they are crossed, the avoided crossing appears. This is a bulk situation. The surface situation is much easier. It is simply the exchange splitting of the topological surface state, because it is at the Dirac point where the topological surface state of a non-magnetic topological insulator is doubly degenerate. So it's kind of Zeeman splitting, normal exchange splitting. Let's say the one state goes down. Let's say it is majority, and the second state goes up. Let's say it's minority, or vice versa. It can be minority, majority. So basically, this is the exchange splitting. I hope I answered all those questions.
I think we can continue.
Okay, great. Thank you very much.
There is a raised hand in the list of attendees, I think.
Yeah, great. So going back to those magnetic heterostructures, I would like to highlight here very interesting experiment that was performed.
Okay, sorry, I have a question.
Okay, go ahead.
Okay, I don't know if you're going to talk about this later, but in the case of magnetic extension, this heterostructure of MBT and BT, what happened? Because at the end, MBT turns out to be topological also, no?
Yes.
So I wonder what happened, because you expect to have these topological surface states in the frontier between two different kind of topologies. But then when MBT is also topological, I was expecting the surface state to be pushed to the end of the heterostructure, as there is no change between bismuth selenite, for example, and bismuth manganese selenite, or bismuth telluride and bismuth manganese telluride. So I don't know why the topological surface state stays there in the interface between the two materials and is not going to the top.
It is going to the top. If we have only one acceptable layer of MBT, topological surface state goes there. That's true. It does not penetrate there completely. That's true. Well, maybe let's say naive explanation would be that the potential from the manganese layer is kind of preventing that, but at least it penetrates up to manganese layer, and there was also a local maximum near the surface. Actually, I will show something similar, but not exactly the same in the following slides. But following back your line of thoughts, if you sandwich two semi-infinite systems, one of them being bismuth telluride, another one being manganese bismuth telluride, that would be very interesting to see what would happen.
Yeah, that's
I have no clear answer to that right now, but that is very interesting to be studied for sure.
Because in this sense, this thing of magnetic extension, I was expecting this from a material that looks like bismuth telluride, but it's not topological.
It doesn't really matter with one susceptible layer, because it is not topological. It is trivial. You have to at least apply some external electric field to make a single susceptible layer of MBT topological. That's the reason. And double susceptible layer will not have much different effect either in this sense.
Okay, because it's only one.
Exactly. In that case, it is only one.
Okay.
I guess I have to continue to cover all the topics that I have prepared for you. Thank you for the question. So in this experiment, the initial intention was to grow randomly manganese doped bismuth selenite. Yeah. But what Hagman and co-workers have discovered by doing TEM, transmission electron microscopy, is that there are blocks that are thicker than quintuples. Namely, they were found to be manganese bismuth selenite septupolayer blocks. The structural sketch is here. I borrowed it from the Nature paper, which I will cover in the following slides. What happens there is that instead of chromium and vanadium that typically have 3+ state in these BST compounds, therefore they readily substitute bismuth or antimony, manganese is typically 2+, and the tendency for the substitution is much less pronounced, although there is substitution, but it is largely suppressed, and therefore the model of this epitaxial film growth was proposed like this. First, you start throwing 3 components simultaneously, but manganese stays at the surface of the growing bismuth selenite film until its amount is not enough to form a complete septuple layer, or almost complete one. And then it proceeds in the same way. You continue depositing, and manganese always stays on top until the next septuple layer is formed. And this is how this random heterostructure has been completed. Later on, namely a couple of years later, a thorough study of the electronic and magnetic properties of such heterostructures followed, both for selenite and telluride case. The telluride case appeared to be much more interesting because it has out of plane easy access. By the way, both heterostructures were found to show ferromagnetic properties. This is the telluride case. You see that hysteresis for out of plane direction of the magnetization is much more pronounced, out of plane field direction, sorry. Both systems were found to be TIs, at least in the sense that there was Dirac cone measured with Rps. More strictly, it would be topologically non-trivial, because for these systems, there is no topological classification as far as I know. And for the telluride system, the Dirac point gap was found to be sensitive to temperature, meaning that it is a magnetic gap of truly magnetic origin. The gap at 1 Kelvin was 90 electron volts based on this EDC decomposition. Well, actually, this is the EDC, this is kind of sketch. And at 20 K, the gap disappeared. And this was reported by groups of Günther, Springolz, and rather. Going back to 2017, once again, there was a nice epitaxial growth experiment that grew a heterostructure sort of magnetic extension. What they did is they first grew the bismuth selenite thin film epitaxially, and using MBE, better say, and then they deposited a nominal bilayer of manganese and selenite on top of it, and due to some self-organization process, manganese and selenium atoms do not stay at the surface, they rather penetrate inside, and a single septuple layer is formed of the MBS composition, as was confirmed by the analysis of the LEED low energy electron diffraction measurements. Actually, I have forgotten to mention here, there was one paper in Applied Physics Letters in 2015, I think, and this paper really grows from there, because their initial intention was to grow manganese selenite, bismuth selenite, sharp interface without penetration of manganese and selenium, but back then the result was not understood in that publication. Then Toru Hirahara and co-workers worked out this thing. Actually, manganese selenite and bismuth selenite sharp interface was recently reported, I believe, in Chinese physics letters, but I have not included this result due to the lack of the space and time. So, of course, for this system, the Rps measurement was performed. This is the Dirac cone of the pure bismuth selenite, and this is the Rps for the heterostructure sample. It is not very clear from here, but maybe you can see there is a hint on the Dirac point gap, which is more clearly seen in the second derivative representation of this photo emission intensity data. Dirac point gap was varied between 85 and 100 milli electron volts. They performed the initial calculations too, and they found that it is in a good agreement with the experiment. So this looks like kind of magnetic extension. Going back again to this kind of systems, but now entering in the two-dimensional limit, not just placing a single septupole on top of the semi-infinite surface of a topological insulator, but organizing these kind of sandwiches, like a number of quintuple layer blocks of bismuth telluride sandwiched between two layers of MBT. Actually, if you carefully calculate the electronic structure of such systems, you will end up with the conclusion that they are the quantum anomalous Hall insulators. For example, this is visualized for the two spacer of two quintuples sandwiched between the two MBT films. So the Chern number is equal to -1, so one conduction, chiral conduction channel, and the conductivity is quantized to E²/H. And basically, last month there has been archive preprint where molecular beam epitaxy was used to grow precisely one of such sandwiches. This is the Rps spectrum of this system. You cannot say much about the Dirac point gap from here, but if you extract the energy distribution curve exactly at the gamma point, it will look like this, and then you perform the careful fitting. At the composition of this curve, you can see that this shoulder here is actually hinting at the gap, and indeed the analysis, EDC analysis, shows that there is a gap about 75 ± 15 milli-electron volts at 4 Kelvin. Formally, this system is a quantum anomalous Hall insulator, but in practice, the Fermi level appears to be in the conduction band, so we have to lower it down either by adding antimony or improving the growth technology to avoid defects, because obviously if the Fermi level is so high there are defects. I have a couple of questions via the chat. Mahima is answering. Sometimes magnetic doping is not breaking TRS and no gap opening is found. So what is the reason behind it? Maybe at least two reasons that immediately appear to me. First of all, in plane, magnetic moment would not necessarily open the gap in the Dirac point, but it would, if there is a magnetically ordered state, there will be the time reversal symmetry breaking, and you should see it in the electronic structure somehow. Or if there is no collective magnetic state in the system, you can have magnetic moments there, but there will be no effect on the topological surface state. Nutachai is asking another question. Do I understand correctly that bismuth 2 manganese selenium 4 is an antiferromagnetic insulator and manganese is a cause of breaking TRS? Yes, manganese is a cause of breaking TRS, and the system is antiferromagnetic and most likely even topological insulator. I will show you this data in the following slides. Thank you very much for asking these questions. So I proceed. Yeah, what else can we do with this kind of experiments when we deposit magnetic atoms on the surface of these TIs? Inspired by the growth protocol developed by Hirahara and co-workers, we have thought that what if we continue depositing manganese and selenium atoms on top of first manganese bismuth selenite septupole, and then we deposit more and more and more. Will we end up having something like that when a magnetic insulator is sandwiched between the remnants of the surface quintuple layer of a TI? As you can imagine, the answer is, of course, yes. And I will try to show you why. What was done basically is the comparison of the total energies always for two situations. First situation, you leave the bilayer of manganese selenite, in this case, on top of the block, surface block, whatever block it is, quintuple, septuple, nonupole, etc. And another situation is that you incorporate this bilayer inside the block. And each and every time, the incorporation was much more favorable energetically by about 0.6 electron volt per manganese selenide bilayer. And moreover, it was found that the encapsulated film adopts its bulk-like structure and bulk-like magnetic ordering. And actually, the same happens with the other two interfaces, meaning that first, this interface is universal, at least, or let's say, let me call it, this situation is universal first, at least for the binary magnetic insulators. And second, this is not a magnetic extension. Why it is not? Because magnetic extension is something, it happens when we really deposit a block of a compound, which is block-weighted compound in this case, on top of the compound with a similar structure, composition, lattice constant, etc. This block is a compound, which is manganese bismuth 2 selenium 4. This block that has 4 bilayers, so therefore, no, it's eight bilayers. Sorry, it would be like manganese 8, bismuth 4, tellurium, whatever. It is not a compound. You cannot grow it inside. And the fact you cannot grow it, sorry, in the bulk form, but you can do such a thing, and when you incorporate it, they acquire bulk-like structure, bulk-like magnetic ordering. So this is a kind of a hint that they are actually some special kind of interfaces, which we call soft interfaces, because they borrow many of nice properties from the magnetic extension, soft interface. This is why I write it in these curly brackets. And another funny thing about this is that the material which has has nothing to do with van der Waals bonding, which is manganese selenite, manganese telluride, and europium sulfide, appears to be somehow van der Waals connected to the topological insulator beneath, not directly, of course, through these remnant bismuth and selenium layers, but nevertheless, this gives the smooth interfaces quite nice properties. For example, you do not have this strong interface potential. You don't have this trivial interface states. And actually it looks like a magnetic extension, but the gap is smaller. Okay, so, and a bit later, this theoretical design has been achieved in experiment. In this case, it was manganese telluride 4 bilayers incorporated inside the quintuple layer block of bismuth telluride. You can see that this is the bismuth telluride film. These are quintuples. If you count carefully, you will find that they are quintuples. But this block is really fat, and moreover, the intensity here is much smaller, hinting that these elements are lighter. Namely, manganese is the most lightest element in the system. This is the zoom in to this structure, but just from the slightly different perspective. And you can see that the stacking is first ABC, pretty much as in bismuth telluride, and then it goes like AB, AC, like in manganese telluride in bulk, and then it goes once again ABC, ABC, like in MBT 1 to 4, or yeah, something like that. And therefore, because there are 2 types of stackings involved in manganese atoms, there are 2 types of magnetic ordering, at least as we reveal in ab initio calculations. It is challenging to determine exact magnetic ordering from the experiments, at least so far. Of course, the Rps measurements were performed. This is the pristine bismuth telluride, and this is the heterostructure. And if you extract the energy distribution curve from the gamma point, you can see that with bare eye, there is a 2-peak structure that later, as measured at 16, later it evolves with a temperature in the following way, and it kind of disappears at about 250 to 90. Yeah, and this is how it looks like in a different representations for 2 different samples. Actually, there have been 4. All of them were showing gaps of 40 to 75, depending a little bit on the sample, probably on the intermixing, because there was one. Yeah, so this is so far the results about the magnetic heterostructures, and now the question is whether some of them can show the quantized topological effects. Of course, we should get rid of the free carriers on the Fermi level first. Now, intrinsic magnetic topological insulators. Let's start with an antiferromagnetic TI. The concept of it was first introduced in 2010 by Monk, Essin, and Moore. It can be realized in insulators breaking both time reversal and primitive lattice translational symmetry, but preserving their combination, which gives rise to the Z2 topological classification. This slide is just to show you that not all of the antiferromagnets meet this combined symmetry. For example, in 2 dimensions, these two do meet, while this non-collinear 120 degrees structure does not. But I will give you a more specific example in the following. Pretty much as the time reversal symmetry in ordinary TIs, the S symmetry in IFM TIs protects the Dirac node at the surface. Namely, if the surface respects this symmetry, it's going to be gapless, but it will be gapped each and every time when it breaks the surface and there is a non-zero magnetization component perpendicular to it. And actually, the latter case is the most interesting one because it represents the ideal platform for observing TME, what would be equivalent to observation of the actual insulator state. As of middle of 2018, there was no FMTI confirmed experimentally, but MBT compound was already published, at least in some form, magnetic extension or bulk material back in 2013 by Korean group. So yeah, what one needed to do is to take it and study first magnetic ordering, and this was first done by calculating Heisenberg exchange coupling constants for both intra and interlayer exchange coupling, as is shown here, those red and blue guys. For the interlayer exchange coupling, the dominating exchange coupling parameter is J01 parallel, which couples two neighboring magnetic moments. It is positive and it is dominating, meaning that there is a strong tendency, relatively strong tendency for the ferromagnetic ordering within manganese layer. While if you carefully analyze the situation for the interlayer exchange coupling and you go sufficiently far away to take into account a number of required number of magnetic parameters for the interlayer coupling, you will end up with a conclusion that the neighboring layers are coupled anti-ferromagnetically. And on top of that, the magnetic anisotropy was found to be perpendicular to the manganese layers in ab initio calculations. And the mechanism of the magnetic coupling in this system is Anderson superexchange. Then you should proceed basically with answering the question whether this material, let's say, falls within this Z2 classification, whether it meets this combined symmetry. So let us consider this. In the non-magnetic case, the T1/2 is obviously a symmetry because it takes one manganese atom and sends it to the neighboring manganese layer. But it is not a symmetry in the antiferromagnetic ground state, because if you take this orange guy with moment pointing down, you translate it to the neighboring layer where all atoms have moments up, it's not a symmetry. But if you apply after the translation the time reversal symmetry operator theta, you flip the spin. So you translate it, you flip the spin, and this is how you nicely recover this antiferromagnetic structure. So the answer is yes, it is a symmetry, but is it an insulator? Yep. The band gap is about 220 milli-electron volts, and then it falls under the Z2 classification of antiferromagnetic insulators, and we can calculate the Z2 invariant based on the parities of the occupied bands, and this is how you can confirm that the Z2 invariant is equal to 1, meaning that the bulk band gap of the material is inverted, which can later on be confirmed by the direct calculation of the density of states as a function of the spin orbit coupling strength lambda. Here at 100% we have the band gap of about 220, which gets smaller and smaller and smaller until it closes at 67.5%, sorry. and then it reopens back in the trivial non-inverted regime. So yes, this material is antiferromagnetic 3D Ti below TNL, and therefore its surfaces should host termination-dependent topological surface states. And indeed, this is the case, for example, for this 0001 surface, which is both natural cleavage surface of this material and S-breaking termination. The Dirac cone is gapped by about 90 milli-electron volts, while for this S-preserving surface, which is basically the side surface, it's a little bit oblique like this. It's not vertical. These are the indices of the surface. It is gapless as it should be for the antiferromagnetic Ti phase. And then, of course, the crystals have been grown. The Rps measurements were performed. I believe Hendrik Bentman in his talk, maybe the day after tomorrow, I don't remember exactly who he will give more information about the Rps because he is a specialist. Here I would like to, just to highlight that the first result indeed showed the Dirac point gap. This is the synchrotron radiation, and yeah, this is the proof of the Dirac point gap in the EDC representation. But if you change the photon energy, you can visualize the bulk valence band, bulk conduction band. And I will also comment in several slides about the issue of the gapless or gapped Dirac point gap, sorry, Dirac cone of manganese bismuth, right? Let us first go into 2 dimensions and consider in the present slide the magnetism. Actually, nothing surprising happens here, but it is important to comment these differences. Since it is layered van der Waals material, nothing basically changes, at least from the theoretical point of view, with its magnetic structure. A single septuple layer is a 2-dimensional ferromagnet. Then for more than one, you have antiferromagnetic interlayer exchange coupling, but the ground state is either compensated antiferromagnet for the even number of septuples or uncompensated antiferromagnet for the odd number of them. And this is very important for the topology because while the single septuple layer block is just trivial insulator, the double septuple layer block is not boring in sense that although it is Chern equal to 0, it is kind of topological state as well, because if you first, to understand what it is, you first need, for example, to achieve or model the ferromagnetic polarization of the system like this, and then you will calculate the Chern number and you will have the Chern equal to 1, and here is the single chiral mode at the edge of the sample. Actually, this result means that in its magnetic ground state, which is collinear, collinear, of course, compensated antiferromagnet with Chern equal to 0, it is nothing else but zero plateau quantum anomalous Hall effect. What is this? This is the intermediate state that is achieved during the remagnetization process. When you go from magnetization up, Chern +1, magnetization down, Chern -1, through the intermediate state, which is the compensated antiferromagnetic state, Chern equal to 0. Why it is so important? Because the zero plateau quantum anomalous Hall state was proposed some 5 or 6 years ago to be a good platform for realize the actual insulator state. By the way, MBT appears to be one of the, as far as I know, first material that realizes the zero plateau quantum anomalous Hall state intrinsically. And then for 3 septuple layers, there is intrinsic quantum anomalous Hall state. It doesn't require any application of the external magnetic field. And then it goes like in an oscillated fashion, depending on the odd or even number of the block. It is either quantum anomalous Hall or a zero plateau. And recently, this was indeed confirmed in experiment. For example, this zero plateau quantum anomalous Hall state and 6 septuples as it is shown here, reported in Nature Materials. They directly called axial insulator state. Well, there may be a debate about that, whether it's sufficient in terms of thickness. I'm referring in particular to the recent preprint by Lawrence Mollenkamp group. But anyway, this is the realization of the zero plateau quantum anomalous Hall state. And also, if you apply external magnetic field, in this case of about 9 Tesla, you achieve full ferromagnetic polarization, which results in the onset of the Chern insulator state with the quantized resistivity, Hall resistivity of H over E square. Actually, this is a new type of Chern insulator because it shows quantized Hall effect, is better to say, not quantum, but quantized, although it's quantum in origin. To not confuse with von Klitzing, right? The quantum Hall effect, we typically refer to the result by von Klitzing and co-authors. Quantized Hall effect under external magnetic field, but no Landau levels, in contrast to the von Klitzing quantum Hall effect, let's say. And similar results on the quantized Hall reported here, who was also able, Denk and co-authors were also able to achieve truly intrinsic quantum anomalous Hall effect that is without external magnetic field. You can see that here the Hall resistivity is practically perfectly quantized, while the longitudinal resistivity is suppressed, almost although not perfectly, but anyway, the hallmark of the quantum anomalous Hall effect is here. I would also like to highlight this publication actually in the following slide, where the Chern number equal 2 state reported under the magnetic field up to 10 Kelvin. This is an impressive result. And Chern number equal to 1 is also reported up to 30 Kelvin. So manganese bismuth telluride appears to be a very promising platform for the observation of a number of Hall effects. Actually, 6 of them have already been confirmed, or let's say claimed to be confirmed. In this case, I refer to archive publications. And there are some pending quantum Hall effects. For example, this half integer quantum Hall effect, whose artistic representation is shown on the left with the characteristic step edges modes that are chiral. Now a little bit about the gapless or gapped. So as I have already said, the first synchrotron radiation Rps studies reported gapped Dirac point, as you can see in these publications. This is the one of the spectra. But then people have found that laser Rps works in a sense better for manganese bismuth telluride, because you can see that the quality of the dispersion map or intensity map is superior clearly, but at the same time, and to a large surprise, the Dirac point gap looks absent or strongly suppressed, as it is reported here. And without entering into details of why could it happen, there is a plenty of literature and plenty of discussion in these papers, because basically the reason is not established today. But I would like to emphasize that even with laser Rps, it is not always the case, because lately, as far as I see from the literature, the point of view of the gapless Dirac point, Dirac cone of MBT is becoming to be generally accepted. I would like to highlight this publication. I'm sorry. Where with laser Rps you can have a Dirac point gap of about 60 milli-electron volts, or in the samples from the same batch, from the same chemist groups, you can also have suppressed Dirac point gap, or at least which does not exceed 20 milli-electron volts. These are, of course, second derivative representations of the photoemission data. The conclusions about the Dirac point gap magnitudes are made based on the EDC analysis that is presented here. On top of that, if the quantum anomalous Hall effect is observed, there is necessarily a Dirac point gap. But in those transport measurements, it is estimated to be below 1 MeV, at least in those measurements and in those samples. What does it tell to us? That there is a huge potential for improvement for manganese bismuth, right? The current observation temperature of quantum anomalous Hall effect is about 1.4. It seems like the quality of the samples is an issue. If we are able to improve it, we will be able to go higher in temperature. This is my feeling about this issue. And then if once you have achieved and established the growth protocols, both epitaxially or using Bridgman growth method of the MBT 124, you can start to play a little bit with growth conditions and achieve other compositions, such as 147, 1610, etc. You can actually intercalate up to 6 quintuples in between 2 septuples, and that would be a bulk single crystal. Yeah, at least the reports reach, current reports experimentally reach up to 6 quintuples incorporated here. 147 and 1610 are antiferromagnetic TIs. There is still the interlayer exchange coupling in this case, but as you can see here schematically, for 3 and more quintuples, the coupling is almost negligible, and therefore there appears some sort of a new topological insulator phase in which below the critical temperature, magnetic critical temperature, the magnetizations of the non-interacting 2D ferromagnets, septuples of MBT, are disordered along the third direction. And finally, if you apply the external magnetic field, you will reach the enforced ferromagnetic state at some point. And for systems with bismuth telluride quintuples, you will achieve a so-called ferromagnetic axion insulator state, which is a sort of a high-order topological insulator state, as reported in this publication. These are the electronic structures measured by laser Rps from these two stoichiometries, 147, 1610. I think I don't have much time to go into details here. I just would like to highlight the recent result about the quantum anomalous Hall effect in manganese bismuth tellur 16 system that was observed, as far as I remember, from the paper for up to 6.5 Kelvin. Looks like a record for the quantum anomalous Hall effect so far. Talking about other systems in particular, we have touched already in the conversation the system which is called manganese bismuth selenite. Actually, the funny thing about this system is that in bulk single crystals, it was always monoclinic, and monoclinic structures give you quite large fundamental bulk band gaps, and so it is not a topological insulator. But if you perform total energy calculations, you can find that this MBS system has the same crystal structures MBT, at least from the point of view of energetical favorability, because this structure has lower energy. The same applies to MST, and both of them, at least in the idealized crystal structure model, appear to be interlayer antiferromagnets, while this MSS guy is monoclinic and therefore topologically boring. Monoclinic in agreement with experiment. So, and very recently, there has been a Nanoletters paper about this manganese bismuth selenite. Sorry, it is indeed made of septuple layers. That is the predicted trigonal structure, which is achieved using the molecular beam epitaxy in thin films. And it is an antiferromagnet, as you can see by the magnetization curve, and the magnetic staggered magnetization easy axis is locked within the manganese plane. And of course, the Rps was performed, although in this case at 80 Kelvin, which is above the nil point. But you can see here there is the topological surface state. And a bit earlier, Choudhury and co-authors predicted that this system is an antiferromagnetic TI. I think I have a question in the chat. What is the difference between axial insulator state and TI? I believe this is about the high-order topological insulator state. Well, TI, as I explained in the beginning of this talk, basically has topological surface states. Depending on whether the TI is magnetic or not, these states might be gapless or not, or depending a little bit on the termination, as you have seen. But this high-order high-order topological insulator state, which is axion insulator, is something relatively new. It's something that has hinge states, not surface states, but hinge gapless states, and it has quantized magnetoelectric response in bulk. So please consult the reference given in the slide. In the meantime, I continue. Thank you for the question, by the way. As I promised, I will tell a little bit about this in plane or planar antiferromagnetic TIs case. In this case, the Dirac point is not gapped, but it is rather slightly displaced from the gamma point, as you can see here. I hope you can. And now let us imagine that we have a magnetic domain wall at the surface of such a material. This could be either due to a septuple layer morphological step at the surface, or naturally due to the formation of magnetic domains. In the case, if the magnetization of those domains are pointing in the opposite directions, what will happen in each of the domains is that the Dirac point gap will displace from the Dirac point, which is not gapped, will displace from the gamma point, but this will happen in the opposite directions. Let's say for this green domain, go to the left, for the blue domain, it will go to the right. But since this is the same surface, somehow these two electronic structures belonging to the different domains should be connected. And the connection appears exactly at the domain wall in the form of this flat band connecting the two Dirac nodes of the corresponding Dirac cones. I think I have one more question from Rafael Vidal. Hi, Rafael. From theory, one expects a gap closing of the TSS above Tn. In the Rps studies of MVT, plenty of which you referenced, there is an absence of any large temperature dependencies of the gap or gapless TSS. Do you have an explanation or educated guesses for? Sorry, do you have an explanation or educated guess? Sorry, for this discrepancy between theory and experiment? Well, there was an explanation in that Nature paper, 2019, that this could happen due to the strongly anisotropic spin fluctuations that are present in these materials. They are not very typical, but for this material, they are present. Honestly, I do not know whether this is the ultimate reason or not, but we will see. Yeah, I completely agree with you. Typically, you do expect that the topological surface state is temperature sensitive in the magnetic material and magnetic topological insulator, like any band of any magnetic material would be. Actually, if I remember, one of the papers from the St. Petersburg group, Rps papers, the topological surface state, actually in the Nature paper as well, does show certain response to the change of the phase, I mean, an antiferro-ferro transition, but that's true, it doesn't close completely. So this is my answer to this question. Thank you very much for asking. And yeah, I'm almost done. I'm just left with manganese antimony telluride, there has been a discussion. Well, actually, it was not a discussion first. From the DFT point of view, it seemed like this material is topologically trivial. Here, I would like to highlight that I'm not talking about manganese antimony intermixing in the present slide. Let us suppose that the system is ideal from the crystal structure point of view. Then if you take the experimental lattice parameters and the experimental positions of the atoms, irrespectively whether there is intermixing or not, typically there is, and you perform the DFT calculation as it is reported here, you will find that in the ground state, which is antiferromagnetic, it will be trivial topology, trivial insulator. And in the ferromagnetic state, it will be either trivial insulator or wild semi-metal. Obviously, it depends a little bit on the calculation parameters. Then basically the same thing will happen if you optimize the structure of this material, but you do not take the van der Waals coupling into account as reported here. You will have basically the same answer. Actually, if you do optimize with van der Waals corrections, you will end up having the antiferromagnetic TI phase and wild semi-metal phase, as it is shown here in this slide. So this is how the bandgap inversion appears. Bandgap value versus the spin orbit coupling. The bandgap is inverted. There is a topological surface state. It is split because this is 0001 surface. It is S breaking. There is a non-zero magnetization from manganese, etc. While the ferromagnetic state is a wild semi-metal. You see, it is there is no gap. There is a crossing and wild point along both gamma plus Z and gamma minus Z, which is not shown. And you can think also about this family of materials, which is pretty similar to those of MBT. And actually, there has been a recent experiment, I think this period actually this month. If you're interested, please check it out. What about the intermixing? Because typically there is. It was found that it promotes the interlayer ferromagnetic coupling. It is confirmed both experimentally and theoretically. So, but let us now imagine a situation when your composition experiences certain variation across the thin film or single crystal, for example, because the fact is that in this material, the interlayer exchange coupling is very weak. Therefore, a small change of the composition will affect it towards one way or another. It will be either ferro or antiferro. So let us imagine that instead of completely ferromagnetically polarized system, you have some portion or some parts of the sample that are coupled antiferromagnetically, where the septuples are coupled antiferromagnetically. So there you will immediately open the bulk bandgap, which will be inverted because you are basically moving from the ferromagnetic state towards antiferromagnetic state, which is antiferromagnetic TI. This is on the hand of the, let's say, of the magnetic coupling. But on the other hand, if you have too much intermixing between manganese and antimony in your system, you will drive your system in the topologically topologically trivial insulator case, as it is reported here. And I believe I do not have much time, almost no time. So there is a experimental confirmation of the magnetic topological insulator case. I do not say ferromagnetic or antiferromagnetic. It is magnetic because it seems to be that there are both anti and ferromagnetic couplings are present. Ferromagnetic couplings seems to be dominating. As you can see from this hysteresis loop, there is a Dirac cone and there is a spin polarization measured by spin Rps. So if you're interested, please check this out. And these are some of my take-home messages. So quantum anomalous Hall effect, which is the fundamental and practically important effect, which could be practically important, right? If it is observed at higher temperatures, presently is realized in magnetically doped TIs and MI-TI interfaces and intrinsic MTIs like MBT Also, it is observed in the twisted bilayer graphene, but I have not included it here. Still, the observation temperature is low, at most 6.5 K without external magnetic field. Manganese bismuth telluride has a big potential for increase of the temperature because of its large Dirac point, at least in theory, Dirac point gap, and new temperature of 25. So there is still a margin, as you can see. MST looks interesting as well because of its Curie temperature that can reach about 45, 50 kelvins in the actual films, and the gap is reported to be about 16 MeV, at least based on STS of these MBE films. Unfortunately, topological magnetoelectric effect in MTIs is still to be observed. So there are reports of axion insulator state, but the final proof of that would be observation of the topological magnetoelectric effect. And finally, MBT or its films are also interesting for topological Hall effect. There has been a recent preprint claiming fermions. You can realize flat bands, high Chern number, high order topological superconductor state, or topological crystalline insulator state. So with this, I'm done, and thank you very much for your attention.
Thank you very much.
Some questions. Do I have time to answer them?
Yeah.
Okay. So then I proceed.
So do you want to try to answer some of the questions in the Q&A session?
Yeah. Why not? So can I proceed now to answer these questions?
Yes.
Okay.
Yeah.
So Aristide is asking, I'm not sure I understood the details of your DFT calculations, and maybe you answered this question already, sorry. DFT is very bad at predicting gap energy. How did you solve this issue in TI, where the band gap is very small? I do agree with you that it is very difficult to carefully describe the band gap of especially unknown or new material in DFT. Basically, what we did in this case is doing a lot of benchmarks varying the Hubbard Q parameter, because it not only affected the position of the 3D states of Magnetization, it also affected the fundamental band gap value. So basically, a lot of tests, and if everything is consistent, then you are more or less okay. But eventually, the final answer will be given by experiment, of course. You can also try to use some hybrid functionals, or maybe the best option would be GW type of calculations. Those are known to be very reliable for these kind of things. Next question by Sotiris. What is the reason that quantum anomalous Hall effect doesn't appear at TC? Well, basically at TC or near TC, better say above TC, the topological surface state would be gapless, ideally, right? So the collective ferromagnetic state or antiferromagnetic state disappears. The state becomes paramagnetic. There is no exchange splitting of the Dirac point if we're talking about the topological insulator. Or if we're talking about any other two-dimensional system that could have quantum anomalous Hall effect, the exchange splitting of the bands disappears, and this could have two outcomes. It is rather a trivial two-dimensional insulator or a quantum spin Hall insulator. But I'm not sure that you can observe quantum spin Hall phase at high temperatures. Maybe in tungsten diselenite, as far as I remember, it is 100 Kelvin, but it is not magnetic. Anonymous attendee, does it mean that all the high order TIs are axes? I don't think so, but I'm afraid I cannot be more specific on that. How to tell if it is axis from experiment? By the way, bismuth bismuth, pure bismuth is, I believe, a high order TI. It has these hinges. I'm not sure whether it is axion insulator, to be honest. But anyway, you have to calculate, in theory, you calculate this Z4 invariant, no mu invariant introduced recently, more or less. And in experiment, there has to be some way found to measure these hinge modes and at the same time confirm that the surfaces are gapped. That would be my question, or my answer, sorry. Satiris once again, what I meant is why there is a big difference between the TC and the temperature that quantum anomalous Hall insulator appears. Well, with the magnetically doped systems, everything is quite clear, because although they have some relatively large TCs, for example, these modulation doped systems, they reach TCs of 80 kelvins. By the way, little parenthesis, this modulation doped system may be a better ferromagnet because those quintuple layers are heavily doped, much more heavily doped as compared to the case when you dope the whole film completely. So they may be better ferromagnets. But going back to your question, because of the intrinsic disorder coming from both random distribution of bismuth and antimony, and then on top of that you add chromium, which is distributed randomly as well, the electronic properties are fluctuating from point to point on the surface. Dirac point gap is location dependent and strongly, and its center is also location dependent, and basically the global gap is very small. This is the picture with the magnetically doped system. With magnetic proximity effect, I think that the trivial interface states still might be at play in that zinc telluride heterostructure doped by chromium. Fortunately, the quantum anomalous Hall effect is observed, but not at very high temperatures. So there might be an issue with trivial states. And also, I'm not sure that the Dirac point gap is large in that case, because magnetic proximity effect is it's not so easy to induce large Dirac point gap with this approach. With manganese bismuth telluride, the exact reason is unknown as far as I know at present. Maybe somebody will correct me. I believe the quality of the samples is the issue, because in the publication by Yambo Zhang's group, the Deng in Co-authors and Science 2020, actually when they first posted their study on arXiv, there was no truly quantum anomalous Hall effect reported. There was only quantized Hall effect under external magnetic field, but they then added this new data that they acquired in the meantime, in between the posting and publishing, posting on arXiv, right? And they explicitly stated that the sample that shows quantum anomalous Hall effect was likely to have a better structural quality. So that would be my answer.
May also have a question. I understood that there is a variety of gaps there. Some people report gapless, some other people report gaps in this material, in the MBT material. Some other people report larger gaps. I was wondering, does it have to do with the thickness of the sound interaction between the top surface states and the bottom surface states, and you may have a hybridization and therefore an opening of a gap that can be seen in Rps. Could that be an effect of thickness, all this variation in the gaps?
Well, in the most simple picture, the interaction between the two surfaces of a film of a topological insulator made of septuples would for sure disappear above 8 septuples. Those laser Rps data, and actually those synchrotron radiation Rps as well, those data, they were acquired on the bulk single crystals, so they are, let's say, infinitely thick as compared to the 8 septuple layer thick film. But when I was listening to your question, I remembered that maybe about 8 or 7 years ago, there were papers by Annika Black-Schaffer and Balatsky, Alexander Balatsky, who studied the issue of the Dirac point gap opening, or let's say something, or appearance of something resembling the Dirac point gap in the TIs with defects or disorders. So they were studying the effects of the impurity resonance levels. And as far as I remember, there has been a claim based on their calculation that those impurity resonance states, they can even provide interaction channel between the surfaces, but I'm not 100% sure, so do not take it as let's say correct, 100% correct information. By the way, something like this happens exactly with manganese bismuth selenite based heterostructures, because Oliver Rader group, they have shown that the gap in the Dirac point is large. Maybe it's about 100 or more milli-electron volts. It maybe doesn't respond to the temperature changes, and I think the resonant photoemission spectroscopy data do detect the resonant manganese states in that system in the region, exactly in the region of the Dirac point. And this is why it is gapped. It seems like this is not the case in MBT, manganese bismuth telluride, or related heterostructures.
Okay. Thank you very much. So, are there any other questions? If not, then perhaps we can have a break here, a coffee break, and then resume at 4. So, in almost a quarter of an hour from now. Is that okay, Sergio?
Yes, perfect. See you at 4.
Yeah, okay. Okay, good. Thank you very much. Thank you. And thank all the attendees.
Thank you, Misha.
Thank you very much.
Enjoy very much your talk.